So you've probably heard about the programming language Rust, right? It's been making a lot of waves. In this explainer, we're going to get into it. We're not just going to look at what Rust is, but really dig into the why. What makes it so different, and why so many developers are getting excited about it. All right, let's jump in. This quote from the official book, it just nails it. This isn't just about learning some new syntax. The whole philosophy here is about a shift in what a language can do for you. It's about giving you the power and the confidence to build things that maybe you would have shied away from before. For the longest time in programming, you had to make this huge trade-off. You could get insane performance with languages like C or C++, but you were on your own with memory management, which meant you were always risking crashes or nasty security bugs. Or you could go with a language like Python or Java for safety and convenience, but you'd lose all that raw speed. And then Rust comes along and basically asks, hey, why do you have to choose? That's a massive promise, isn't it? Combining the absolute best of both worlds. So how in the world does it pull it off? Well, the secret sauce is this really unique and powerful concept. And if you can get your head around this one thing, you'll totally get Rust. And that one thing is called ownership. I'm telling you, if you grasp this one core idea, everything else about the language just starts to click. It is the engine that makes all of Rust's safety guarantees possible. Okay, so to really get ownership, we got to do a super quick refresh on how programs use memory. There are two main parts, the stack and the heap. The stack is super fast, super organized, kind of like stacking plates. It's perfect for data where you know the size up front. The heap is more like trying to find an open table at a busy restaurant. It's way more flexible and can handle data that grows and shrinks. And yeah, that heap, that's where things can get messy. It's where the bugs love to hide, and it's exactly the problem ownership is here to solve. So here's the kicker. Ownership isn't some background process like a garbage collector buzzing away while your app is running. Nope, it is a set of rules that your code gets checked against before it even becomes a program, at compile time. If you follow the rules, your code compiles. If you don't, it just won't. Simple as that. And what's amazing is how simple these rules are. There's just 3 of them. First, every single value has an owner. Second, there can only be one owner at any given time, no sharing. And third, the second that owner goes out of scope, like at the end of a function, the value it owns is automatically cleaned up. That's literally it. 3 rules that change everything. Okay, so what does this actually look like in your code? Let's check it out. For simple stuff on the stack, like the number 5, if you assign it to a new variable, it just makes a copy. Both x and y are good to go. But for more complex data on the heap, like a string, when you assign s1 to s2, you don't copy it, you move it. Ownership has been transferred and S1 is no longer valid. And just like that, Rust totally prevents one of the most classic, nasty bugs out there, the double free, because it's now impossible for 2 variables to try and clean up the same piece of memory. This is where a lot of people have that big aha moment with Rust. The compiler isn't this mean thing that just yells at you. Think of it less like a gatekeeper and more like a super smart, kind of strict, but ultimately really helpful tutor. It enforces those ownership rules, and by doing so, it literally teaches you how to write better, safer code. So instead of your program just blowing up on some poor user at runtime, you get a clear message like this while you're still coding. This specific error stops something called a data race, which was when 2 parts of your program try to change the same data at the same time. The compiler just won't let you do it. It's almost like having a little guardian angel on your shoulder, catching bugs before they're even born. So you put all this together. The rules, the compiler checks, and it all leads to this one huge payoff, a feature that the community has famously dubbed fearless concurrency. And I mean, this is the big one. Data races are an absolute nightmare to debug in multi-threaded code. But in Rust, because the compiler knows exactly who owns what and who's allowed to change it, it can mathematically prove that data races are impossible in safe Rust. An entire category of nightmare-inducing bugs just vanished. Poof, gone at compile time. And this brings us right back to that idea of empowerment we started with. You can actually write code that takes full advantage of modern multi-core processors without that constant nagging fear that you've made some tiny mistake that's going to bring the whole system down. It's a total game changer. Okay, so Rust totally rethinks memory, but it doesn't stop there. It also has a really interesting take on how we structure our programs, especially when you compare it to classic object-oriented languages like Java or C++. I love this comment from a developer online because it really cuts through the noise. People are always asking, so is Rust an object-oriented language? And the answer is kind of, well, it's complicated. It takes some of the good ideas, but it throws out one of the big ones, classical inheritance. So let's break that down. Rust says no to what we call implementation inheritance. That's the idea that a class can just inherit all the code and data from a parent class. Instead, Rust says yes to interface inheritance using something it calls traits. A trait is like a contract. It defines a set of behaviors, like anything that is a shape must be able to calculate its area, but it's up to each individual struct to actually write the code to fulfill that contract. It's a subtle difference, but it pushes you towards a more flexible design. All right, so Rust gives us this incredible new model for building safe, high-performance software. But it's a living, breathing language, right? It's still evolving, and with that evolution comes some really interesting debates about its future. And one of the really hot topics in the community right now is this. As Rust starts adding more high-level features like async for network programming, is it a natural, good evolution, or does it risk making the language too complex and losing some of that low-level clarity that made it so special? You've got some developers, like this one, who are a little worried. Their concern is that by trying to be both a deep systems language and a high-level application language, Rust could be building up a kind of design debt that makes it harder to learn and work with down the road. But then, of course, there's the other side of the coin. Plenty of others see features like async as a vital evolution. Sure, maybe the implementation isn't perfect just yet, but it's a critical tool for building the kind of software we need today. It's just another way Rust is trying to empower its developers. And what this all boils down to is the central tension at the heart of Rust's future. It's this constant balancing act. How do you keep adding powerful, modern features without chipping away at the very foundations of safety and control that make Rust, well, Rust? Which really leaves us with this huge question, one that's bigger than just Rust. In the entire world of software, can you really have it all? Can a language give you maximum power and maximum safety without eventually collapsing under its own complexity? There's no easy answer, but Rust is one of the most fascinating attempts to find one, and its journey is definitely something worth watching.